Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, as we discussed in the last class, that we will be starting a new topic or new chapter, okay, which will deal with the deflection due to bending, as you can see from this slide. Deflection due to bending, integration of the moment curvature relationship for simple boundary conditions and a method of superposition, and then finally, we will be moving to the energy method that will be coming later on. So, now what is the, as you have seen when we were discussing about the bending theory, then you have seen that the straight slender member you had, and after bending it was taking this kind of shape where concave, I mean of course, depending on the type of bending moment, positive or negative, depending on that you will be getting the curved shape of the slender member, right. So, because of this bending, actually you are getting the deflection. Deflection means you had the straight beam and then it got deflected. So, from the neutral position or from the original x axis to the final after deformation what is happening. So, this is nothing but the deflection, right. So, that deflection can be estimated by using or by establishing the relation between the moment curvature. Okay. So, now let us see how we can establish that relation by which we can find out the deflection in the beam due to bending. Okay. The moment curvature relation. Okay. So, now as you recall, so this is so this was your neutral axis. Okay. So, this is the beam after bending, okay, and see this angle which is made at the center, say phi, and the radius of the curvature, say rho, okay, and this is under pure bending situation. We will be already we have seen that thing earlier, pure bending situation, say. So, the original x axis was horizontal and this is the curved part. So, this angle is basically this angle, okay. That means, the departure from the original x axis will give you the relation between the deflection. Deflection means the originally it was horizontal and now it has got the curved shape. Okay. So, this angle will establish the relation between your deflection and the curved shape. Okay. So, now, so if I draw the line diagram basically, so this was the original position, okay, and then after deflection or after deformation, after the application of the bending moment, it takes the shape like that. So, this is nothing but your slope, right. At any point, if you consider at any point on the curved line, okay, you can find out the slope, right, and that slope will be varying, right, at each and every point of the beam, the slope will be varying, and that we can establish or we can derive or we can get some say some relation by which we can find out the slope at each and every point. So, now in the xy plane, basically if you look at, so this was the original configuration horizontal. Okay. Now, it takes the shape like that. So, therefore, this much is your deflection. So, dV, this was your say dx if I consider, and this is your ds along the curved part. Okay. So, along this curved part, if I dashed line or the dotted line, if I consider ds and this is the say dx. So, this much is the departure dV, and this angle is say, this angle automatically will be phi as per the definition. Okay. Here is the angle made at the center. Okay. So, now the slope of the neutral axis, the slope of the neutral axis is nothing but dV dx equal to tan phi. Very simple, because this is your say neutral axis. Okay. So, dV dx is nothing but the slope of the neutral axis. Okay. So, now if I differentiate both the sides with respect to the curved surface ds, then I can write d ds of dV dx equal to d ds of tan phi. We are taking or we are doing the differentiation with respect to curved length ds on both the sides. Okay. So, this can be written as d2v dx2 dx ds is equal to sec square phi d phi ds, say equation 1. Agreed? Fine. So, I have got this relation. Now again we know from our earlier discussion that 1 by rho is equal to d phi ds is equal to mb by ei zz, right. Already we have established this relation. If you go back to the previous lecture, you will see already we have established this relation. Okay. So, now, so from 1, if I put this relation in equation 1, we will get it. So, d phi ds, okay, is equal to d2v dx2 dx ds cos square phi. Okay. Now, from the figure, whatever figure I had drawn, the figure means that one. So, this was your dV, this was your dx, and this was your ds, and this is phi in xy plane, right. Now, in that figure, we can see cos phi is equal to dx ds, okay, which can be written as 1 by 1 plus dV dx whole square to the power half. So, from where this relation is coming? This is simple geometrical relation, because as you know cos phi from your trigonometry 1 by 1 plus tan square phi to the power half, that you know, right. From trigonometric relation, this thing is known to me. Okay. So, I can write that cos phi is equal to this. Now, I am substituting that thing here. So, what I will get? Therefore, d phi ds is equal to d2 v dx2. Now, dx ds cos square phi is nothing but cos cube phi, right. and cos cube phi is nothing but cube of this. Okay. So, therefore, I can write 1 plus dV dx whole square to the power 3 by 2. Okay. So, this is equation say 2. Okay. Now when the slope angle phi is very small, because generally in this kind of slender beam or slender member, right, you cannot, I mean, this phi is very small, the slope angle is very small, right. So, therefore, we can say dV dx is also small, okay, and dV dx whole square can be neglected. Okay. Therefore, from that equation 2, I can simply write d phi ds is approximately equal to d2v dx2, which can be further written as, now what is this d phi ds? This d phi ds is nothing but mb by ei zz is equal to d2v dx2. Okay. So, or we can write like this. So, ei zz d2v dx2 is equal to mb, right. This is nothing but your moment curvature relation. Now, what does it mean actually? What does it interpret? So, if you know the bending moment, and though the equations, all the equations are valid for your pure bending, but already if you recall in the previous lectures we agreed that whether it is pure bending situation or if you have the constant shear force or the varied shear force, this still whatever theory we have developed for pure bending, that will be holding good, right. So, based on that we can say that any situation where you have shear force also, varying shear force also, then in that situation also this equation is valid. Okay. So, now what does it say? It says that if you know the bending moment applied in the slender member, and if you know this EIZZ, so there is some special name for this EIZZ. So, EIZZ is nothing but your, it is known as flexural rigidity or bending modulus. Okay. So, this is for a particular section and particular material, EIZZ is constant, right. If you consider a constant cross section of the slender member, and if you consider a constant, I mean homogeneous material in the slender member, then EIZZ is constant. So, this is the flexural rigidity, this is known as flexural rigidity in mechanics or bending modulus in some books that also mentioned. Okay. Now, so this part you can calculate from the material property as well as the cross section of the beam or the slender member, right. So, once you know this, and once you know this how much bending moment is getting applied, you can find out or you can solve this differential equation to get V. What is V? V is the deflection, that is the departure, as I showed in the figure, right. V is the departure from its original horizontal position to the curved part. Okay. So, this V can be obtained from by solving this differential equation with proper boundary conditions. Okay. Now, let us take one numerical problem or example, so that you will be understanding also that how we can solve this kind of problem. Let us take that problem. Okay. Let us take one numerical problem. So, you will appreciate that how we can find out the deflection from the moment curvature. The problem is like this, very simple problem we are taking to understand this thing in a better way. You have a simply supported beam, reaction R A and R B. So, this is point A, point B. You have one concentrated force W here, okay, which is acting at a distance away from A, and this is B. The total length of the beam is say L. Okay. And okay, fine. So, for this actually your objective is to find out the deflection as well as the slope at the point where the load is applied. Okay. So, your first, what is your first job? As already we have done several times, your first job is to find out the external reactions R A and R B, and you know how to find out that R A will be coming as W B by L and R B will be coming as W A by L. Now, to define this whole beam, how many minimum sections you need to take? 2, because there is one load. So, from this point to this point there is no variation of load, then from this point to this point there is no variation of load. So, we are taking 2 sections, section 1 1 and section 2 2. Okay. Now, based on that we are going to find out the bending moment and shear force. Okay. So, section 1 1. So, that is nothing but this. This is your V, this is your MB, this is your RA and this is your X. So, from this I can find out MB equal to RAX is equal to WBX by L, fine. Similarly, section 2 2, if we consider, we are considering this part, left hand side part. Okay. You have RA, you have W which is acting a distance away from A, and you have shear force here, bending moment, okay, and this distance is say x now. Okay. For that your MB can be calculated. Okay. I am not going through the stepwise calculations, that you know how to find out MB. So, MB will be coming as Wx B by L minus 1 plus W. Okay. So, I have got MB for section 1 1 and MB for section 2 2, and that is, both equations are defining the total variation of bending moment over the whole beam, right, over the whole beam. Okay. So, as we know, this is my moment curvature relation. I am not writing IZZ every time because it is quite understood. So, I am just writing simply EI. Okay. So, for I mean now onward I will not be writing IZZ again and again. Okay. Fine. So, this is my moment curvature relation. So, now for section 1 1, if I apply this moment curvature relation, I will get EI d2v dx2. Okay. This is equal to what? Bending moment. What is the bending moment in section 1 1? That is the bending moment. Okay. So, that is WBX by L. Very simple. Okay. So, now if I integrate this, EI dV dx is equal to WB x square by twice L plus some integration constant C1, say equation 1. Okay. Similarly, I will be getting one more integration EIV, that is the deflection I have got, okay, that is WB x cube by 6L plus C1 x plus C2 is equal to equation 2. Okay, now C1, C2 they are not known to me and they can be found out from the boundary conditions, suitable appropriate boundary conditions. Okay. So, this is the expression which will give you the deflection for section 1 1. That means, if you are traveling from point A to this point, within this point your deflection can be defined by this equation. And similarly, what is this? This is nothing but your slope, is not it? This is nothing but your slope. Okay. So, now similarly, we will do the same exercise for section 2 for section 2 okay, EI d2v dx2 is equal to bending moment, that is MB for section 2 please try to remember. So, that already we have calculated Wx b by L minus 1 plus Wa. So, now I integrate once, that will give me W x square by 2 b by L minus 1 plus W a x plus C 3, say the equation 3 say, and then one more integration will give me E I v W x s cube by 6 b by L minus 1 plus W a x square by 2 plus C 3 x plus C 4 equation say 4. Okay. So, I have got 4 equations to be solved. Okay. First, we need to find out all the integration constants C1, C2, C3, C4, and you know how to find out from simple mathematics. Okay. So, let us find out those constants by putting the suitable boundary conditions. So, what are the boundary conditions I can think of? So, you need at least 4 boundary conditions, right? 4 boundary or the continuity conditions you need to find out all 4 unknown integration constants. So, first thing is that at x equal to 0, I can say v equal to 0, that is the displacement is 0 simply at x equal to 0 for that beam, because that is the support condition, right. At x equal to 0 means at point A there is no deflection of the beam. Similarly, at x equal to L your v equal to 0, right. Now, by putting this from your equation 2, I can simply get C2 equal to 0, at least one integration constant has been found out. Okay. So, same process if we perform for other equations from equation 4, we can write down this W L cube, equation 4 means this equation. Okay. This equation will be giving me the deflection from this point to point B, in between that it will give me the deflection. So, if I put x equal to L here, so I will get the deflection at point B, which is nothing but 0. So, I can write W L cube by 6 B by L minus 1 plus W A L square by 2 plus C 3 L plus C 4 equal to 0. So, from this if I do little bit of simplification, finally I will get C 3 L plus C 4 equal to minus W A L square by 3, so equation 5 I am saying. Okay. So, that I am getting. Okay. I am getting one relation between C3 and C4. Okay. Now, at x equal to a, at x equal to a means you are at this point, say this point say D. Okay. At x equal to a, that means when you are at point D, then basically V coming from section 1 1, that means if you solve the equation of V means your deflection for section 1 1, that should be equal to the V calculated from section 2 2. Well, that is a continuity thing, because at the same point the beam bending is continuous, right. At the same point you will not be getting two different deflection of the beam. So, whether you come from section 1 1 or from section 2 2, at that particular point, that is a common point D, at that point your deflection should be same. So, that I am writing. So, V coming from section 1 1 and V coming from section 2 2 at x equal to a must be same. So, if I put the values of V for section 1 1 at x equal to a is nothing but W a cube by 6 B by L minus 1 plus W a cube by 2 plus C 3 a plus C 4. So, from this I will be getting one relation C 1 between C 1 and C 3, C 3 a minus C 4. Okay. I am getting the relation among these three constants equal to W a cube by 3. Say this equation, say equation 6. Okay. Now, by following the similar argument, I can say at x equal to a, your slope of the curve must be same, whether you come from section 1 1 or section 2 2. Okay. So, what I can write dV dx calculated from section 1 1 is equal to dV dx calculated from section 2 2. They must be same, deflection has to be same at point D, whether you come from 1 or 2, as well as your slope will be same. So, if you put the equations for that, W b a square by twice L plus C 1 is equal to W a square by 2 B by L minus 1 plus W a square plus C 3. Okay. So, by simplifying this thing, I will be getting C 1 minus C 3 equal to W a square by 2. Say equation 7. So, you have got 4 equations, okay, and 4 unknowns. So, from which you can find out the magnitude of your integration constants. So, I will stop here today. In the next class or the next lecture, we will be solving all the, or we will be finding out the magnitude of all the integration constants, and then we will impose some special condition to find out the slope and deflection at point D. Okay. So, I will stop here today. Thank you very much.